Hi students, so in this video I'm going to solve a problem which involves a storage tank 2 meters wide which has a vertical partition across its width. Side 1 of the partition is filled with oil with a density of 900 kg per meter cube to a depth of 1.8 meters, and side 2 is filled with oil with a density of 750 kg per meter cube to a depth of 0.9 meters. Find the resultant hydrostatic thrust on the partition. So in order to solve this problem, first of all I'll draw a diagram which will help me solve the problem. So I'm going to draw my tank. Now this tank has a partition in between. So that's my partition. And it has on one side fluid filled with oil of density 900 to a depth of 1.8 meters. So I'll say this is roughly 1.8 meters. You don't have to draw this diagram with a scale. It's just to give you a clear explanation. I'm using a scale. If you are asked this question in your exam, you're better off drawing a rough diagram just with your hand to save time. So here we got a tank with a partition in between. Now this is liquid 1. And that's liquid 2. This has a height of 1.8 meters and this has a height of 0.9 meters. Now what other information do we have? We have the density of the two liquids. So I'm going to make a note of all the given information first. Liquid 1, liquid 2. So height H1 is 1.8 meters, H2 is 0.9 meters. We have the density of liquid 1. Density is represented by the symbol called rho, and that is 900 kg per meter cube. That's rho 1. And density 2 is 750 kg per meter cube. We've noted the depth. Now in order to solve this problem, I have made a small visual aid of what this tank will look like and what is the hydrostatic pressure that you have to calculate. So imagine a tank which is 2 meters wide, so that is 2 meters, and this is 2 meters as well, and it has a partition in between, and this is filled with two liquids. This side is filled with one liquid to this level here, the other side is filled with another liquid to that level there. And just for you to visualize this problem, now how do you find the hydrostatic thrust? So hydrostatic thrust on side 1. So I'm going to find the hydrostatic thrust on this side here. So that's going to be hydrostatic thrust F on side 1, and I have another hydrostatic thrust F on side 2. We have to find F, or the hydrostatic thrust on side 1. So F side 1 will be equal to, where do you find a formula to find the hydrostatic thrust? So you again refer to your formula sheet, and at the very last page you've got fluid principles, you got a section for fluid principles. Hydrostatic thrust on immersed plane surface is given as rho, g, a and x. So I'm going to use this formula. F is equal to rho, g, a and x, where x is the height for a rectangular plane. Now x is the height on which the average pressure will be acting. So if I have a liquid at a height of say 1.8 meters, the average pressure of the hydrostatic thrust will act at a point which is halfway between here and here. So this x will be equal to height of the liquid divided by 2. So we will get two values of x. In this case, my x1, or the point at which my hydrostatic thrust is acting, will be equal to h1 by 2, and x2 will be equal to h2 divided by 2. That is going to be equal to 1.8 divided by 2, which is equal to 1.8 divided by 2, 0.9 meters, and this is going to be equal to 0.9 divided by 2, 0.45 meters. So now we have made a note of the x. A stands for the area. Now x, I said, is the height. A stands for area. Now what area do we need? If you take the tank here, we need to find the area. So if this is my tank, storage tank, we need to find the area of this surface, all this here. And this area on the other side. First of all, we are going to find the area of this surface here on side 1. This is my side 1. That's side 2. We need to find that area there. So how do you find the area? To find the area, you need height times the width, which is across here. Now we've been given the width of the storage tank. The storage tank is 2 meters wide. I'm going to make a note of the width, 2 meters. So it is 2 meters wide. So from this point to this point is 2 meters. So we will end up with two areas. So area 1 will be equal to height 1 times the width of the tank, which is from this point to this point, and correspondingly area 2, that is this area here, will be equal to height 2 times width of the tank again. So this is going to be equal to 1.8 times 2, and this is going to be equal to 0.9 times 2, which will be equal to 1.8 times 2 is 3.6 meters squared, and this is going to be equal to 0.9 times 2, 1.8 meters squared. 1.8 meters squared will be area 2. That's area 1, that's area 2. That's my tank here. I've got my hydrostatic thrust formula for side 1. Again, this is going to be rho 1. G is acceleration due to gravity. Now the value of G will be equal to 9.81 meters per second squared. Now the value of G is again in your formula sheet on the very last page. G equals to 9.81 meters per second squared. So you don't have to remember it, but as you solve many problems you tend to memorize it. So always remember G is 9.81 meters per second square. So now F1 will be, my density 1 is 900 times G is 9.81 times area 1 will be 3.6 times X. X here we have calculated as 0.9. So force on side 1 will be equal to 900 times 9.81 times 3.6 times 0.9. 28,605.96. 28,006. Oops, it's 605. 605.96 Newton. So that's force hydrostatic thrust on side 1 calculated. Now let me calculate the hydrostatic thrust on side 2. I'm going to keep this aside here. Hydrostatic thrust on side 2 will be, again, Fs2 will be the same formula, but it's going to be density 2, gravity will be the same, times area 2 and x2. So now we substitute the values of all these quantities in my equation. My density 2 is 750 kg per meter cube, so 750 times gravity is 9.81 times area 2 we have calculated here as 1.8 meters per second square times x2 is equal to, we have calculated it here as 0.45, and that's going to be equal to 750 times 9.81 times 1.8 times 0.45, 5959.57. 5959.57 Newton, which is Fs2. Now if you consider my tank here, the question is asking you to find the resultant hydrostatic thrust on the partition. So if I was to consider my partition here, and just look at the partition this time. It has a force on side 1 acting on this side here from left to right with a force of 28650.96 Newton going in this direction, acting at a point halfway between. So exactly halfway it's going to act over here, 28650.96 Newton, and on side 2 it's going to I'll get a hydrostatic thrust or a force acting in this direction again at a length half of 0.9, because we calculated the x value at which the hydrostatic force is acting halfway between 0.9 in this direction. So what is going to happen is the net force acting on this wall will be equal to, let me get rid of this, keep the problem here, the tank, the net resultant force will be equal to Fs1 minus Fs2, which will be equal to, if you take a look at the figures, Fs1 is 28605.96 minus 5959.57. So I'm going to enter the values over here, 28605.96, take away 5959.57. The answer is 22,646.21. It's going to be 22,646.21, and I'm going to name this, say, FR, and FR will be 22,646.21 Newton going from left to right, because this side has a higher pressure acting on that side, and hence the net force will tend to go from left to right, from left to right. So that's my answer. It's a good practice to highlight your answer. So again, if you have a liquid filled up to a height of 1.8 meters with a density of 900 kg per meter cube, and on the other side you have a liquid filled up to a height of 0.9 meters with a density of 750 kg per meter cube, the net resultant will be acting on side 2 going from left to right with a force of 22,646.21 Newton. And that's your solution. Now what I want you to do is close this video and try to solve the same problem without looking at the video. Good luck.